Hello, my name is Matthew and I've been doing Vex IQ for the past several years. Last year at Worlds, my team got 19th place at the programming skills, so there's a lot I'd like to share with you about programming. In this series, we're going to talk about how to make a competition-ready and competitive autonomous program, focusing mostly on the navigation. To start off, I'm going to share with you how to create a basic autonomous program with the baseline Vex IQ movement options. So in the VexCode, first click add a device, then we're going to select drivetrain, and after that we're going to select the ports for the left and right wheels. So I'm just going to select 1 and 2, and then after that we need to select if we don't have a gyro sensor, if we have a gyro sensor, and if we're going to use a brain inertial instead of the gyro sensor. I'm just going to select a gyro sensor. And then once you create the drivetrain, a whole new menu will pop up. You see there's drive forward for 200 millimeters. You can change that to any number you like. There's turn right for however much you want, turn to whatever heading, and turn to whatever rotation. So in essence, there's only 2 movement options, and that's drive straight and also turning. So with these basic movement options in mind, what I like to do next is kind of just write out the general structure of what I want my route to look like. So I can draw it out, or I can just write down basically what I want to do, and then I can plug it into the VexCode, and it's a lot easier because I already have all my thoughts written out, so I just need to plug in the numbers and test the code. So now let's talk about sensors. The gyro sensor and the brain inertial sensor are both great ways to help the robot tell which way it's facing, and also they're super important when you're designing a PID. So the gyro sensor works for both Gen 1 and Gen 2 brains, but it takes up a motor slot, so you might want to be careful about that. While the brain inertial sensor only works for Gen 2 brains, but it's built into the actual brain, so it doesn't take up a slot. And also, for the brain inertial sensor, on top of telling the heading and the rotation of the sensor, it can also tell the acceleration of a certain axis, the gyro rate of a certain axis, and also it can tell the pitch, yaw, and roll. Well, another thing to keep in mind when you're deciding if you want to use a gyro sensor or a brain inertial sensor is how much space you have in the center of the robot. So both of these sensors work the best when they're in the center of the robot, because that's where they're the most accurate. As you see, for this robot, we decided to use a gyro sensor because there's not that much space in the middle to put the brain. So I think we should have designed the robot around the brain instead. Same for this one. There wasn't that much space in the middle, so we had to put the brain out here. So then it wouldn't be super smart to use the brain inertial, since it's not super accurate when it's on the side. So that's why we also use the gyro sensor for this robot. One more thing to keep in mind when you're deciding if you want to use a gyro sensor or a brain inertial is that the gyro sensor reports a counterclockwise positive heading. So as you see here, it goes this way. The 90 degrees is on the left, and it continues to get bigger this way. But for the brain inertial, it's the other way around. So for some people, it might feel more intuitive that 90 degrees is on this side, while for some people, it might be the other way. They might think 90 degrees feels better on this side. So that's one more thing to keep in mind. But also, if you want your gyro sensor to report the headings like the brain inertial, like you want the gyro sensor 90 to be on this side, you can just flip the gyro sensor over upside down, and then the 90 will be on this side, just like the brain inertial. How accurate are the baseline movement options anyway? According to the official Vex IQ website, all smart motors have a built-in PID that precisely control the output speed and the rotation of the motors. So that means the baseline movement options are also directly controlled by this built-in PID. So with that in mind, you think that the baseline movement options are pretty accurate, right? And it is for most of the time. So in our experience, we found that the baseline movement options are pretty reliable for when you just want the robot to move straight. But when you want the robot to turn, there's a lot more factors to it, so that becomes a different story. So unlike most other vehicles like bikes, scooters, and cars, Vex IQ robots solely depend on the difference between the left wheel speeds and the right wheel speeds to actually turn. For example, if you want your if you want your robot to turn left, then you'd have to have your left wheel go slower and your right wheel go faster. That makes it pretty hard to make precise turns consistently. But like cars or scooters on the other hand, they only need to steer the front wheels, and that guides the rest of the vehicle behind it. So that makes it a lot easier to make precise turns. So in our experience, we found that the baseline movement options for turning gets the robot to around like 4 to 6 degrees off from the wanted angle, which is not too great. But let's say, for example, in an autonomous route, every turn was within 1 or 2 degrees, which is pretty precise. Even if every turn was within 1 or 2 degrees, the amount that the robot would be off by would still compound and grow exponentially. So by the end of the route, the robot would still be off by a lot. So that's why we have to come up with a different kind of thinking and come up with a different kind of architecture. So we know that making small and precise turns consistently with the Vex IQ robot is pretty difficult. So instead of thinking that we have to make the precise turns every single time, instead we can think about it this way. So if you want your robot to turn to 120 degrees, but it accidentally overturns by like 6 degrees, so it goes to 126, then the walk after you turn to 126 will fix the robot's heading and make it face towards 120 degrees again, because it's easier to make small precise turns or like fix the amount it's off by on the walk after. So even if the robot hits something or it just overturns or underturns, the walk after the turn will fix it. So now I'm going to show you how to create this architecture yourself in the Vex IQ code. So the first thing we need to do is add the left wheels and the right wheels as motors. So left wheel, and then also right wheel, and then also I'm gonna add the gyro sensor for when we're making the PID, and also a touch LED to act as a button when we start the program. And after that, I'm gonna create a my block called walk heading. And then walk heading angle. So this variable is gonna be the angle that you can just put in. And then I'm gonna add a label, distance. So we're adding a distance variable. And then I'm going to create another my block called turn to for the turning. So turn to angle. And also, instead of using the distance, I'm going to add a boolean, which is basically asking true or false if you want to turn clockwise or counterclockwise. So there we go. This is the basic architecture for our PID. And then after this, I'm going to create a my block called route 1. So it's really good if you split up your entire autonomous run into like a few different routes. So that'll make it easier to test it, because you can just run the individual routes instead of running the whole entire run just to edit like one little part. And then also it makes it a lot easier to read, because for example, you could just make route 1 turn to angle like 90, just put a bunch of random stuff, But then when you actually want to run it, you can just do one touch LED pressed, run route 1. So that makes it a lot easier to read and helps organize your code. So finally, we want to initialize everything and set all the motor velocities, so then the program will run at its best. So when it says 1 started, we need to set the max torque and max velocity for all the wheels if you want it to go the fastest it can and the most efficient. So right wheel, so left wheel max torque 100, left wheel max velocity 100, right wheel max velocity 100, right wheel max torque 100. And then we wanted to play a sound to let the person know that it's done calibrating. So we're gonna do sound, add a siren. Oh yeah, and I almost forgot, we have to also calibrate the gyro sensor for it to work the best. Calibrate for this many seconds. And there we go. This is the basic architecture for our autonomous run. So in our next video, we're going to talk about how to create the actual PID that will make the robot walk and turn very precisely. And yeah, there we go. Thank you guys for watching. So here are some of the topics that I hope to cover in the following videos, like actually designing the PID for making the robot walk precisely, making the robot turn precisely, helping the robot control the speed correctly, strategies for corrections, and everything down here. So I need your guys' support. So if we get this video to 20 likes, I'll make the next video on how to actually design the PID to make the robot walk accurately.